So fossil fuel combustion is basically taking a jolt from that battery of the biosphere. We're digging up some buried organic carbon and reacting it with oxygen to get the energy back. So one thing that may occur to you is, does that mean we're going to use up the oxygen in the atmosphere? That would be like draining the battery of the biosphere all the way dead. Fortunately for us, most of the buried organic carbon in the Earth is in an inconvenient form to use as a fuel. Limestone rock is a big white thing, but it has maybe a few tenths of a percent of organic carbon mixed in with it in a form that we could never extract and put into a gas tank. So most of the buried organic carbon is not suitable as a fossil fuel. So there are three basic types of fossil fuels. And the most abundant of them, and therefore the most important one for the future of Earth's climate, is coal. So coal is fossil plant material that was protected from being respired by being deposited in a swamp. So if you have a soil that has lots of water, it's very waterlogged, it's hard for oxygen from the air to get down in there. And so plant material, leaves, roots, or mosses can accumulate as thick deposits of very pure organic carbon known as peat. And then when that peat is cooked, it matures into what we call coal. So there are two different sort of types of coal. Coal that is produced, that is formed in saltwater conditions, tends to have more sulfur in it because seawater has sulfur in the form of sulfate. Whereas coal that's formed in freshwater conditions tends to have less sulfur in it. So you already know about the sulfate aerosols. This is where they come from when there is sulfur in the coal that's released to the atmosphere. It makes these little droplets which scatter light, change the properties of clouds, the indirect effect, and all of that. So coal is basically mostly elemental carbon. So the oxidation state of carbon just by itself is zero. So coal is sort of like halfway between the most oxidized form and the most reduced form. So it only has half as much energy per carbon as natural gas, which is the most reduced form of carbon. Coal is also not particularly convenient as a fossil fuel compared to the other ones because it's in a solid form. And so mostly what coal is used for is to generate electricity by burning it and using the heat to boil water to make steam, and then using the steam to drive a turbine, as opposed to oil, which is in a nice liquid form that you can put in a gas tank. So coal is the most abundant of the fossil fuels. Here are sort of approximate inventories of different types of fossil fuels. And these are somewhat fuzzy numbers because how much coal we think can be extracted from the earth depends on how far we're willing to go to get it, and on technological improvements in coal mining, things like that. But in general, there's at least 10 times more coal and maybe 50 times more coal than the other fossil fuels. So the question of what Earth's climate will look like in the year 2100 and beyond depends largely on what happens to that coal. The next kind of fossil fuel to consider is oil. So oil, as you know, is what they make gasoline out of. It's the most convenient fossil fuel. It's therefore the most precious, the most expensive. Oil is formed not from land plants like coal, but mostly from plankton in the ocean that land on the bottom of the ocean and can be preserved in the sediments if the conditions are right. So actually, most sediments at the bottom of the ocean don't have enough organic carbon in them to really make much oil. Oil comes from very special what are called oil source rocks. So the entire oil field in the Middle East comes from source rocks that are just a few feet thick. Very special rocks, very special conditions are required to concentrate organic carbon in the sediments to a high enough degree that you can make oil. Then, after the carbon is deposited in these source rocks, it has to be cooked just right to make oil. There's a depth range in the earth between about 2 and 4 kilometers, which is called the oil window. And if so the temperature gets higher the deeper you get in the earth. So if the source rocks are not buried to a deep enough level, you'll have immature oil, some sort of tar sand, something like that. Or if it gets buried too deeply out the bottom of the oil window, the carbon will be converted to natural gas. And so it's very specific conditions that allow the formation of liquid oil. And then to get it out, most of the oil that's extracted is stuff that has migrated in the sediment column and found some sort of a trap where it can accumulate. So probably most of the oil that was ever formed on Earth just leaked back to the surface of the Earth and was gone forever. But some tiny fraction of it gets trapped in these traps, which are amenable to harvesting. So that's why the inventory of oil on Earth is so much less than the inventory of coal, because of all those unlikely things that have to happen in order for a carbon molecule to end up as oil. So oil is got long chain structures of carbons. And each carbon, because of the number of electrons it has, because of its chemistry, each carbon has to have 4 bonds to it. And so for a simple, this is a hexane molecule. So these carbons on the end have to have 3 hydrogens in order for this carbon here to have 4 bonds, or these ones in the middle have 2 hydrogens each, and then 2 bonds they're to carbon to either side. So if you take the average of the carbon and hydrogens in this molecule, it kind of looks like CH2, which means that it's more reduced than coal. So this has an oxidation state of the hydrogen is 2 times plus 1, and so the carbon is minus 2. So the oxidation state of carbon in coal is 0. Here it's minus 2. So it's more reduced than coal. So you get more energy per carbon molecule for carbon atoms from oil than you do from coal. Now there are 2 different ways of thinking about how long the oil will last. There's one method is to take the reserves to production ratio. So the units of that, you always got to keep in track of the units. They will tell you what's going on. Could be gigatons of carbon for reserves, and then gigatons of carbon per year for the rate of production. That's what they in the industry call extracting oil from the ground is production. So canceling the units, we end up with units of years, and this would be time of how much time until the last drop is extracted that we now know about at the present day rate of production. So if you look at this plot of the historical evolution of this ratio through time, what you'll see is that there's 40 years of oil left, and 40 years ago there was also 40 years of oil left, and it sort of looks like sort of a perpetual motion machine, like there could be oil forever, because if we could discover it as quickly as it's being produced. Another way to think about oil, though, is using an idea known as peak oil. And this is based on the observation that the rate of extracting oil from some oil field, like the state of Texas, for example, tends to follow what's called a Gaussian or a bell curve. This is an empirical relationship. This is an observation. Gee, it kind of looks like this. It could look different. The rate of extraction could look different. But what tends to happen is you have sort of a ramping up period as the infrastructure is getting put into place. And then the rate of growth tends to sort of taper off, and then it starts to sort of come back down. So what this means is that the the implication of this is that the peak comes when the oil is only half gone. So as opposed to over here, we were looking at the last drop. Here, we're thinking about where the peak should be, and if you have demand that's growing sort of exponentially, where the shortage is going to happen is sort of at that peak. So looking at the amount of oil that is thought to exist on Earth today and the history of the oil extraction rate so far, we can use this theory to come up with some estimate of when the peak rate of oil extraction will be. And we're right about close to the peak now. The traditional fossil fuel inventories of oil are about 200 gigatons, and we've already extracted about 100 gigatons of that. So we're about halfway there. So peak oil would say that this is the time when oil is going to start getting more scarce. Natural gas is the third major form of fossil fuel. It's methane mostly. Basically, you can get natural gas from either the sort of coal peat kind of organic carbon or from the plankton oil source kind of organic carbon. As long as it's heated up enough, it sort of cooks and forms some methane. So because methane is a gas, it's more difficult to transport than either oil or coal because it has to be held in a pressurized container. And so it turns out that for that reason, the price of natural gas varies hugely from place to place around the world. There are places in the world where natural gas is worth basically nothing. So it comes out as a byproduct of getting oil, and they just burn it rather than try to keep it. Methane is the most reduced form of carbon, so it has the most energy per carbon released, and it also tends to burn more cleanly than either coal, which makes these aerosols and little particles in the atmosphere, or oil, which tends to leave reactive compounds that make urban smog. So for those reasons, methane is called a cleaner fuel than oil or coal, but it's still a fossil fuel and it's still releasing carbon to the atmosphere. So most of the major gas reserves on Earth are found underneath a sort of impermeable cap kind of rock, either permafrost like in Siberia or salt deposits from evaporated seawater in the Middle East. There's also a vast amount of methane in a very spread out and probably mostly inaccessible form known as methane hydrates in ocean sediments. And so very spread out, but there could be thousands of gigatons of methane as methane hydrates.